This lesson is on basic trig identities, and the main thing that I want you to think of with any identities that we do is that it is using substitution in some way. So think substitution, we're looking for something to substitute in. You already know some of these from using the unit circle. These fractions are called your reciprocal identities. When we use the unit circle, we use the fact that tangent is sine over cosine, but you can also use tangent is 1 over cotangent. In some cases, that might be more beneficial. When you use the unit circle, you say that cotangent is cosine over sine, but again, cotangent is also the same thing as 1 over tangent. That might be useful in some problems that we do. The next two over here, you also again know from the unit circle, the secant is 1 over the cosine and the cosecant is 1 over the sine, but the reciprocal or flips of those also are true. The cosine is 1 over the secant and the sine is 1 over the cosecant. The ones on the left are the ones that you use with your unit circle, and we use those the most, but occasionally these on the right get used. So they're real easy to remember because they are related to the ones on the left, or at least these two are related to each other. So these are things that you need to know and remember. They're not things that are going to be given to you on a formula sheet. I'm also including in these identities Pythagorean identities. There's 3 of them, and that's because they're related to the Pythagorean theorem. And these are sine squared plus cosine squared is 1. 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared. And again, these are things you need to memorize. You need to know these 3. There will not be a formula sheet that gives them to you. Now I have things to know. When you're using those Pythagorean identities, you need to understand what's going on. The sine squared or cosine squared or secant squared, whatever is in the formula, when they put the square between the trig function and the variable, it truly means that whole thing is squared, not just the theta. It's the whole thing squared. It's just this is how it's written in trig language. If you're typing it in your calculator, you need to write it like this, or if you're needing to work with it, you can write it out as sine theta times sine theta. But that's a big thing to understand, is that the square means that it's really the whole thing squared. They just write it like this. Something else that can happen is that you can rearrange the Pythagorean identities just like you were solving an equation. So this first one is rearranging sine squared plus cosine squared equals 1. So if you think about having that identity, to get to this, all they've done is subtract sine squared from both sides, so that they're left with cosine on this side, and then over on the right you have 1 minus sine squared. So they've just subtracted the sine to the other side. The 1 equals secant squared minus tangent squared is really similar. It came from 1 plus tangent squared equals secant squared. And so if you look at the difference between these two, then you can see that all that's happened is they have subtracted the tangent squared from both sides. And so this side on the left became 1, and the side on the right became secant squared minus tangent squared. That is legal to do and use. So when I am substituting, if I have cosine squared and I need to substitute something in, I can substitute 1 minus sine squared. Or if I have 1 minus sine squared in a problem, I can substitute in cosine squared. Because those two are equal, they can replace each other. And the same thing down here. If I have secant squared minus tangent squared in a problem, I can replace that with 1, substituting that in. One very important thing that you need to remember is that you can't drop the powers with the Pythagorean identities. So sine plus cosine is not 1. It has to be sine squared plus cosine squared if you want to replace it with 1. Okay, so the Pythagorean identities must have the squareds in them when you see them in problems. If they don't, then you need to look at your reciprocal identities. Okay, these are my suggestions for when you're looking at these problems. The first thing is look for identities. Decide, is it maybe one of the Pythagorean identities that's just been added or subtracted like we were just talking about, rewritten in a certain way? Or is it one of the reciprocal identities that we're looking at? If that is the case, you can usually just do one substitution and be done. If that doesn't work, usually, this is what I do, is I turn things into versions of sine and cosine. Because, as you know, everything on the unit circle we were able to come up with because we knew the sine and cosine. We can use those identities, the reciprocal identities and things, to turn everything into sine and cosine and see what we can do from there. See if that helps us out. You can also use algebra and do things like distribute or FOIL, or they will factor. When we went over factoring at the beginning of the year, I gave you, I think, a few problems that had trig in them. It factors just like trinomials and perfect squares tend to do. You can multiply by a conjugate if that helps. So like the conjugate of 1 plus sine would be 1 minus sine. And then sometimes you might need to get two fractions together using a common denominator. That's why, again, we went over how to simplify fractions at the beginning of the year. Okay, your goal when you're doing a problem is to get rid of fractions, if possible, which most of the time you can, and to have the smallest pieces possible. Okay, so I'll talk about that more when we're doing the problems. I don't have really another word for that at the moment, but you want it to look as simple as possible. So if there's a fraction, you want to rewrite it so that there's not, and you want, to reduce it as much as possible to something that's workable. Okay, so examples. Okay, so our first two examples are really what I consider classic examples. These are ones where you're pretty much always going to use the reciprocal identities. And I recognize them because it's like a string of trig stuff, and I could even have more than two that are just multiplied. There's no pluses, there's no minuses, there's no fractions. When these things are just multiplied, you want to replace them with the fractions that work in sine and cosine. So cosecant x is the same thing as 1 over sine x. Like I said, this is all about substitution. Cotangent x is cosine x over sine x. Okay, and I just realized that I typed this wrong. I was supposed to type tangent, so I'll finish this, but then I'll show you what I meant to do. In this case, really, cosecant times cotangent is the most simple form, because when I get it here, if you multiply across, 1 times cosine is cosine, and sine times sine is sine squared. And that's still in a fraction. The way that I could undo the fraction is by changing that sine squared on the bottom to be a cosecant squared. So I could write this as cosine times cosecant squared. And really, these two are about the same level of simple because it's just two things multiplied together. But like I said, I didn't mean to start off with this problem. It was my fault. So I'll come over here. What I meant to do was cosecant times tangent, because in that case, when I change cosecant into 1 over sine and tangent into sine over cosine, what can I do? I can cancel out. These signs are diagonal from each other, and just like when I was multiplying fractions with polynomials, I can cancel diagonally. That leaves me with 1 over cosine, and 1 over cosine is the same thing as secant. And so that is a one-piece answer compared to a two-piece problem, and it's simple. Okay, that was the goal, and again, I apologize, but this is how it would have worked on 1 if that had actually been the problem. Okay, example 2, really similar if you want to pause and try it on your own. So what we do with this one is we turn tangent into sine over cosine. Cosine doesn't change. You just have to remember that it's like over and understood 1 if it's not written as a fraction. And then you can cancel diagonally, and that just leaves you with sine x over 1, which is just sine x. And so that's a one piece instead of two pieces, and so it's a lot simpler looking. Okay, so we've had the question, what would have happened if I had changed cosine to 1 over secant? And that would have just made the problem go a little bit longer. If you change cosine into 1 over secant, nothing cancels. And so you end up having sine over cosine times secant. And then you have to change secant into 1 over cosine. So you have sine and cosine times 1 over cosine. And then those will cancel and you have sine over 1. You'll get to the same answer, it's just a lot more work. And that's why I say in my suggestions to turn things into terms of sine and cosine. So if it's already sine or cosine, don't mess with it. But if it's not sine or cosine, turn it into a fraction that has sine and cosine in it. Okay, so I'm going to restart number 3 here. I had a typo, so this should be a plus. So now let's double distribute. So 1 times 1 is 1. 1 times negative cosine x will be negative cosine x. Positive cosine x times 1 is positive cosine x. And then a positive cosine times a negative cosine would be a negative cosine squared. Okay, so again, I'm looking at distributing on this problem because it didn't have any, it didn't fit any of my identities, so I'm needing to move to the algebra part. When I look at what I have now, the two middle terms cancel. That leaves me with 1 minus cosine squared. Now if you look at your identities, what is 1 minus cosine squared the same as? Okay, so if you look at the Pythagorean identity, sine squared plus cosine squared equals 1, and you subtracted the cosine squared, you would be left with sine squared. And you would have sine squared equals 1 minus cosine squared. So you can do this part in your head. But I have the 1 minus cosine squared, it's equal to sine squared. I can replace it with that because they are equal. And then I'm down to one thing, which is better to look at than these pieces up here. It's smaller, it's more compact, it's easier to work with, and that's our goal. Now we're looking at number 4. We have secant squared minus 1. And always the first thing you need to do is look, is this an identity or a version of the identity? So pause, take a moment, look at those identities, and decide, is it something that I already know? Okay, so you should notice that you have the Pythagorean identity, 1 plus tangent squared equals secant squared. And if you subtracted 1, you would have tangent squared equals secant squared minus 1. So this is truly just a version of one of your Pythagorean identities, and I can replace this secant squared minus 1 with tangent squared. Instead of two pieces, I have one, and so this is officially simplified. Okay, so we move on to example 5, and again, always, first step is to look at the identities you're supposed to know and see if this is a version of one of those. I notice that I'm using squareds, so I immediately go to my Pythagorean identities, and there is a Pythagorean identity that says 1 plus cotangent squared equals cosecant squared. And I'm looking for cosecant squared minus cotangent squared, so I think about over here what that would mean. That would mean subtracting the cotangent squared. And so this would be equal to 1, which means in a situation like this, I can replace it with 1. And so that was a really fast, really easy problem because I noticed immediately that it was a Pythagorean identity. If you didn't notice, you would do probably a half a page of work that was not necessary. Alright, number 6. Now, I see a cosine squared, but my sines are not squared. And so this is not immediately jumping out as a Pythagorean identity just moved around. I can turn things into sine and cosine. They're already there. Okay, so I need to think about algebra. Do you see what algebra step I might could take to work on this problem? Okay, so for number 6, we are looking at using algebra, and in fact, it has a GCF. So I want to factor a sine out. That would leave me with cosine squared minus 1. Now when you look at the problem, you see cosine squared minus 1, and you should recognize that as a version of your Pythagorean identity. So what can I replace cosine squared minus 1 with? Okay, well, check again. You have sine squared plus cosine squared equals 1 as that identity. I need it to be cosine squared minus 1. So I need to subtract the 1, but I also need to move the sine to the other side. So I'm subtracting sine squared. So I'm going to get cosine squared minus 1 on the left, but I'm going to have a negative sine squared on the right. So I can replace cosine squared minus 1. It will be with negative sine squared. Now I have sine times negative sine squared. And this is just like having an x times an x squared. You add the exponents. So I technically have 3 sines here, and it's a positive times a negative, so it'll be a negative. And I'll have a negative sine cubed, which is 1 piece instead of 2 or several. Okay, 7, if you look at it, again, you don't see one of your Pythagorean identities. You could turn things into sine and cosine, but you wouldn't get too far. This should remind you of what we just did, because both pieces have a cosecant, and that means I can take it out as a GCF. So I have cosecant x outside. That leaves me with cosine squared minus 1 inside. Now, we just did the work on that, so we know that cosine squared minus 1 is the same thing as sine squared. So I need to bring down my cosecant and replace this with negative sine squared. And again, I got that math from the same thing I did on number 6. Okay, at this point, I know cosecant is related to sine, so I want to go ahead and turn that into 1 over sine. And think of the negative sine squared as being over 1. And I want to do that because I'm trying to get things to cancel. And I can see that I have sine on the bottom and 2 sines on the top. So think of that squared as sine times sine. Again, I have a positive times a negative, so my answer should be negative. I can cancel this sign with one of those signs. So I like to mark out the exponent just to remind me I'm down to 1. And so my answer is negative sine x. Alright, we have 2 more examples. So these get into some fractions. Example 8. Alright, we have tangent plus cotangent over tangent. When the bottom does not have a plus or a minus, this can legally be separated. It's just the reverse of what we normally do when we get a common denominator and put fractions together. Reverse that one step and say that is tangent over tangent plus cotangent over tangent. And again, you're normally working from this step and going to that step, but we're trying to simplify, so this is going to help. Okay, so tangent over tangent is obviously 1. cotangent over tangent, I need to think about using those reciprocal identities. So I can turn them into sines and cosines, or I can use the other relationship, which is what I'm going to do in this case. I'm going to leave the top as cotangent. I'm going to turn the bottom into 1 over cotangent. That's going to allow me to flip and multiply. So I keep the top, I flip the bottom, and multiply. And again, this one's over 1 too, so that gives me 1 plus cotangent squared. This should be something now that I recognize, and 1 plus cotangent squared is one of my Pythagorean identities. I can replace it with cosecant squared. And I'm down to one piece. A lot simpler to look at than the original problem. Okay, I saved the most complicated one for last. When you look at this, you don't see any Pythagorean identities because nothing is squared. That means you have to go to the reciprocal identities and turn these into fractions. And as I usually suggest, most of the time sines and cosines are going to be the best to work with. Example 8 is an exception to that. So I'm going to turn tangent into sine over cosine, and I'm going to turn cotangent into cosine over sine. It still doesn't look like anything I can work with. This is the case where I have to get a common denominator. So again, this is really similar to what we did with fractions at the beginning of the year. It's just we have trig now. So the common denominator between cosine and sine is cosine sine or sine cosine. You got to have both of them. So I'm going to put new fractions with a common denominator. When you do that, you keep the old stuff from the top, but you look at the bottom and see what's new. So from the bottom of this one to the bottom of this one, I have a new sine, so I need to multiply by sine on top. From the bottom of the second one to its new common denominator, I added a cosine in, so I need to multiply by that cosine on top. So it's the same process. Then I write them over one common denominator. Sine times sine is sine squared. Cosine times cosine is cosine squared. And then what do you have on top? You have a Pythagorean identity. Sine squared plus cosine squared is 1. I can replace the entire top with 1. And then you're almost to the answer, because one of your goals is to get rid of fractions if you can. And so you have to look at this as 1 over cosine times 1 over sine, and then replace those using the reciprocal identities. So 1 over cosine is secant, and 1 over sine is cosecant. And this is as simple as this is going to get. It's 2 pieces multiplied, okay, instead of added. Multiplication is always preferable to addition if possible. Okay, and that concludes this lesson.